This lecture presents capabilities of Mathematica for working with units, doing units conversions, and using physical constants. Important to note, for these operations to work, Mathematica requires an internet connection. So to define a quantity with units, you use the function quantity. So here, for example, M is defined as 42 kilograms. The first argument of quantity is the magnitude and the second is the units, and you can see it's here typed in double quotes with a capital letter name for the unit. The syntax for units is somewhat forgiving. You could also use for kilogram capital kg, lowercase kg, and so forth. If you have a quantity with compound units, like a density in kilograms per cubic meters, then you write it like this. So the units here are kilograms in quotes divided by meters in quotes raised to the 3. It almost always works to type that as an equation, so to speak, of the units in quotes. So kilograms per cubic meter, like that. If you want to get the number back, in other words, to strip off the units, then you use the function quantity magnitude. So quantity magnitude of the density I've just defined is 1,000 without the units. If you just want the units, that's quantity unit. To do units conversions, you use the function unit convert. And it has 2 arguments. The thing you want to convert is the first argument, and the units you want to convert it to is the second argument, written in the same way as previously, the units in quotes. So if I want to convert that mass of 42 kilograms to pounds, then this does it, and it's about 92 pounds. If you don't give a second argument to unit convert, then what you get is SI units. So 42 kilograms in the case of the mass in pounds converted back to 42. If you try to convert to units that aren't consistent with the quantity that you've defined, you get an error. So if you try to convert that mass to meters, it fails. Oftentimes you want to convert an entire data set from one system of units to another. In principle, you can give units to data sets. In other words, you can think of a data set as being a list of quantities, each of which has units. Don't do this. It is possible in Mathematica, but it is not a good idea because it's a bit buggy. Plots of data with units don't always work the way you think they should, and calculations on data with units are often slow. But there's really no reason to ever do this. If you want to convert a table of data which is in one set of units to another, then what you need are conversion factors, and it's easy to do that, as I'll illustrate here. So for example, I'm just going to make up a table of data which is a list of pairs, and we suppose, for example, that this is a list of times and positions where the times are somehow in minutes and the positions are in feet. Okay, so suppose we want to convert that to seconds and position in meters. Then what we need obviously are conversion factors, and we can use the functions of Mathematica to produce those conversion factors conveniently. So since the time data are in minutes, we need a conversion factor that converts from the quantity 1 minute to seconds. Okay, I mean that's 60 obviously, but if you didn't know, this will produce it for you. So that's 60 seconds. That's the conversion factor. Each one of those times in minutes needs to be multiplied by 60 in order to be transformed to seconds. And the positions in feet, which we want to convert to meters, then again we want a conversion factor which is 1 foot, 1 feet, converted to meters. And that is 0.3048 meters. So to make the converted data set, we make a copy of it. New data equals data makes a new copy, And then we work on the columns of that data, multiplying each column by the corresponding conversion factor. So all comma 1 in double brackets means all rows the first column of the new data, and we set that equal to its previous self times the first conversion factor with the units stripped off. So quantity magnitude strips off the units and gives me just this 60, and then that will convert the first column of the new data, in other words the time values, from minutes to seconds. Likewise, the second column of the new data, which is all rows second column, is equal to its previous self times the magnitude of the second conversion factor, the 0.3048, but without the meters. And in this way, new data is a set of numbers which have been converted from, oh, I made a typo. So that's new data with a capital letter. That's blue, telling me that it doesn't know what new data is. Now, new data is a list of pairs where the values have been converted to seconds and so forth. One of the nice things about Mathematica working with units is that it can do calculations of quantities that have compatible but unlike units. So if we have two distances here, one of them is in feet and one of them is in centimeters, then I can add them and, for example, convert the sum to meters, or I can multiply them and convert the area that I get to centimeters squared, using unit convert to control the units that the sum or the product is represented as. If you try to do something in incompatible units, in other words, you try to add a length and an area, then you'll get an error and it will echo back what you tried to do. So in addition to dealing with units, Mathematica has predefined the values of a very wide range of physical constants. And to access them, you can define quantities in effect using the constant itself as the unit. So if you need the speed of light, you define a quantity which is 1 in units of the speed of light. And when you do that, you get a strange answer, which is 1 times c. It doesn't specify a system of units. It just says, okay, c is 1 times the speed of light, which is called c. Likewise, m0, if I define it as to be 1 electron mass, the mass of the electron, then it echoes back 1 times m sub e. Okay, it doesn't say this is what it is in grams or kilograms or what have you. You can, however, use c and m0, so defined, in calculations and convert the result to whatever system of units you want. So for example, if you want the energy equivalent of the mass of an electron, mc squared, the Einstein formula, in joules, you just unit convert mc squared to joules, and you get this answer. For chemical engineers, two of the most important physical constants are the molar gas constant R and the Avogadro constant N sub A. And to access those, you simply define R to be the quantity 1 in units of the molar gas constant, and it gives you back, like above, 1 times R. If you unit convert that, in other words, to SI units, you get the familiar 8.314, etc. And it's giving you in SI units. This kilogram meter square per second squared is a joule, right? And so this is joule per mole Kelvin. N sub A, likewise, the Avogadro constant is 1 in units of the Avogadro constant. And if you unit convert that, then you get the familiar 6.02 times 10 to the 23 per mole. So now I'm going to do a succession of examples of using units conversion in various problems. So the first one is how big a house you can build on a given lot. Zoning laws sometimes limit how much of a lot can be covered by the house you build. And if that fraction were limited to 0.2, then how big a house in square feet can you build on a quarter-acre lot? So A lot here is 0.25 acres. I define a quantity to be that. And then I simply want 0.2 of that in square feet. So 2178 square feet. For the next example, how much does the paint weigh on a typical car? So car paint's about 120 microns thick. I'm going to approximate a car as being a sort of rectangular box about 6 feet wide, about 30 inches tall, which is kind of how tall it would be if you squashed the roof down to be level with the rest of the body, and about 180 inches long. So how much does the paint weigh in kilograms, assuming the paint density is about 1, just for this example? So the height of the car is 30 inches, the width is 6 feet, the length is 180 inches, the thickness is 120 microns. Those are all compatible but unlike units. Nonetheless, I can define the volume of the paint to be 2 times the height times the width. That's the front and back of the car, plus 2 times the height times the length, that's the 2 sides of the car, plus the width times the length, that's the top of the car, all that times the thickness. So this is the total area of the paint, and that's the thickness of the paint. And then the density of the paint is 1 gram per centimeter cubed, and then the mass is this volume times the density converted to kilograms. So about 2 kilograms of paint on a typical car. So next, just a simple units conversion problem. The heat capacity of water is a calorie per gram Kelvin, and the molar mass is 18 gram per mole, more or less. So what's the heat capacity of water in joule per mole Kelvin? Well, so here's the heat capacity, CV, written as 1 in calories per grams kelvins. Here's the molar mass of water, written as 18 grams per mole. And clearly the product of those will get rid of the grams and leave moles in the bottom, okay? And it's an energy per temperature times moles. And so I can convert that to joules per moles Kelvin and get about 75 joule per mole Kelvin. So for another heat capacity type problem, so the average kinetic energy of a molecule flying around in an ideal gas is 3/2 kBT, where T is the temperature in Kelvin and kB is the Boltzmann constant. And the heat capacity, C, is defined by how the energy varies with temperature, dE dt. So here what I ask is, what's the heat capacity per mole of an ideal gas in SI units? So I start with the heat capacity per molecule, that is, the temperature derivative of its energy, 3/2 kBT, is 3/2 times the Boltzmann constant, kB. And so here is the heat capacity per molecule, 3/2 times the Boltzmann constant, or in units of the Boltzmann constant. And then I define my Na to be 1 times the Avogadro constant, because I want to convert from number to moles. And so the quantity I want is C per molecule times how many molecules there are per mole, that's Na, and I get 12.4 something. This is joules, kilogram meter square per second square per mole Kelvin. So note that unit convert doesn't give what you might like just for neatness, joule per mole Kelvin, but it's equivalent. Strangely, if we explicitly ask it for joules per moles Kelvin, it doesn't work. This is a bug. If we ask very carefully and nicely, it does work. If we write the joules and the moles and the kelvins all in quotes, then in this particular case that seems to be necessary to get the unit conversion to behave. So this is a problem in a little estimate in solar power. Arizona, a very sunny state, has an area of 113,000 or so square miles. plenty of wide open space and receives solar radiation of about 6.5 kilowatt hours, that's an energy unit, per square meter per day. The entire US uses about 317 million megawatt hours per month of electric power. And commercial solar cells are about 15% efficient in turning solar radiation into electricity. So the question is, how much of all of Arizona would you have to cover with solar panels to, in principle, issues of storage and transportation aside, supply all U.S. electricity needs? So those needs are 317 million megawatts hours per month. The area of Arizona is 113,998 square miles. The energy per area is per day is 6.5 kilowatts hours per meter squared per day. The efficiency is 0.15. So the power, as it were, incident on all of Arizona is the area of Arizona times this power per area times the efficiency. And what we want is the ratio of the total power required to supply electricity to the entire U.S. divided by the total power incident on Arizona. And so that's 3.5% of the land area of Arizona, which is a lot of land, no question, but gives an idea of the potency of solar power as if you were able to, for example, put solar panels on most of the roofs of buildings where people live and work. So for my final example, I'm going to do some estimates that have to do with stop-and-go driving. So a VW Golf GTI weighs about 3,000 pounds. And the first question is, how much kinetic energy does it have traveling at 35 miles an hour? So we'll calculate that in a moment. Then next, we're going to ask how much gasoline in liters has an energy content equal to that kinetic energy if the heat of combustion of gasoline is 45 megajoule per kilogram and its density is 0.77 kilogram per liter. So some quantity of gasoline, some number of liters, some fraction of a liter has an energy content which, if you converted it perfectly to kinetic energy, would be able to accelerate a car from rest to 35 miles per hour. So if the engine were perfectly efficient, this amount of gasoline, as I just described, would suffice to accelerate the car from rest back up to 35 miles per hour. But engines are typically only about 20% efficient, so one may ask how much gasoline is wasted every time you stop the car if you've been traveling at 35 miles per hour, because you've got to accelerate it back up again. And to convert that, how much gasoline is wasted, into some more practical measure, consider that a Golf GTI gets about 40 miles per gallon if you drive it steadily. So how many meters could the car go on that amount of gasoline? Those are the questions I want to answer. So for the first one, here's the mass of the car in pounds, here's the velocity of the car in miles per hour, and here's the kinetic energy, a half mv squared, and I'll unit convert it, which means convert it to SI units. So that's how many joules of energy, 165,000 joules, are in the motion of a car at 35 miles per hour. So now I want to find out how much gasoline it takes so that the equivalent energy of burning it, if you could burn it perfectly efficiently and convert that to kinetic energy of the car, how much gas would it take? So the heat of combustion of the gasoline is 45 megajoule per kilogram, and the density of the gasoline is 0.77 kilogram per liter, and the product of those then is, of course, megajoules per liter, energy per liter, right? So if I want to know how much gasoline then what I need is the kinetic energy I'm trying to get divided by the number of megajoules per liter that the gasoline can produce in principle. And so that volume of gas in liters is quite small, 0.005 liters. If we ask how much gas we wasted because we stopped, then it's 5 times as much as this, because the efficiency of the engine is only 0.2. So the volume per stop of gasoline that we need to accelerate back up again is this volume of gas divided by 0.2, or in other words times 5, because it's only 20% efficient. And so that's this quantity here. And if we take that and say, well, how far can you drive on that amount of gas at 40 miles per gallon, then we define the mileage as being 40 miles per gallon, and take that mileage times this volume of gasoline and ask how many meters you can go on that. And the answer is 400 meters. Which is a considerable distance, and so that you can see then how wasteful it is to have stop and go driving versus being able to drive continuously, because you're having to continuously accelerate and decelerate the car inefficiently.